The universe is a vault holding more secrets than answers. For all our telescopes and theories, the cosmos remains a place of profound mystery. Today we are going on a journey through 30 of the most baffling questions that still keep scientists up at night. By the end, you will see the cosmos not as a map of known stars, but as a frontier of endless wonder. We will confront the invisible substance that shapes galaxies and ask if time itself could flow backwards. What single cosmic mystery do you find the most haunting? Our journey begins with the most fundamental question of all, the very fabric of reality. What is the universe actually made of? If you were to take a cosmic inventory, counting every star, every planet, every speck of dust and wisp of gas in every galaxy, you would have accounted for a shockingly small fraction of what is out there. All of that, everything we can see and touch and measure with light, is less than 5% of the total cosmos. It is a cosmic afterthought, the decorative sprinkles on a cake whose main ingredients are completely invisible and utterly unknown. The rest, the overwhelming 95%, is a profound mystery divided into two shadowy categories, dark matter and dark energy. We know they exist not because we can see them, but because we can see what they do. Dark matter is the cosmic skeleton. In the 1970s, astronomer Vera Rubin was studying how fast stars orbit the centers of spiral galaxies. The laws of gravity tell us that stars on the outer edges of a spinning galaxy should move slower than those near the center, just as the outer planets in our solar system have longer, slower orbits. But Rubin found something astonishing. The stars at the edge were moving just as fast as those near the core. It was as if the entire galaxy was spinning like a solid plate. The only logical explanation was that there had to be far more mass in the galaxy than what the glowing stars and gas could provide. A vast halo of invisible matter whose gravity was holding the speeding stars in place. This missing mass, this ghostly gravitational glue, is what we call dark matter. It does not emit, absorb, or reflect any light. It simply clumps together through gravity, forming the invisible scaffolding upon which galaxies are built. Without it, our Milky Way would have never formed, and the universe would look nothing like it does today. Yet after decades of searching with the most sensitive detectors buried deep underground, we have never directly caught a single particle of it. We are surrounded by an ocean of something we cannot touch or see, a substance 5 times more abundant than everything we know, and its true nature remains one of physics' greatest puzzles. But if dark matter is the hidden scaffolding of the cosmos, dark energy is the phantom force tearing it all apart. In the late 1990s, 2 separate teams of astronomers made a discovery that shattered our understanding of cosmic destiny. They were measuring the distances to extremely far-off supernovae, using them as cosmic mile markers to see how fast the universe was expanding. Everyone expected to find that the expansion, which began with the Big Bang, was slowing down over time, pulled by the collective gravity of all the matter in the cosmos. Instead, they found the opposite. The expansion of the universe is not slowing down, it is speeding up. Some mysterious repulsive force, acting against gravity on the largest scales, is pushing galaxies apart at an ever-increasing rate. This force was dubbed dark energy, and it makes up a staggering 70% of the universe. Think of it like this: you throw a ball straight up into the air. You expect it to slow, stop, and fall back down because of gravity. But instead, the ball starts moving upward faster and faster, as if the sky itself were pushing it away. That is what dark energy is doing to the fabric of space. We do not know what it is. It could be a property of empty space itself, a constant energy woven into the vacuum. Or it could be something far stranger, a dynamic field that changes over time. What we do know is that its ultimate victory seems assured. If dark energy continues unchecked, it will lead to a cold, dark, and lonely end for the cosmos, where distant galaxies vanish over a cosmic horizon, leaving our descendants, if any remain, with a sky nearly empty of stars. So the universe is built on a ghostly skeleton and driven by a phantom force, neither of which we understand. This brings us to a question that haunts us here on our tiny, illuminated island of normal matter. With hundreds of billions of stars in our galaxy alone, and most of those likely hosting planets, the numbers scream that we should not be alone. The math is almost unbearably compelling. Astronomer Frank Drake once framed this optimism as an equation. Start with the rate of star formation in our galaxy, multiply by the fraction of those stars with planets. Then by the number of planets in each system that could support life. Then by the fraction where life actually emerges, and then where that life becomes intelligent, and finally, by the length of time such a civilization might broadcast detectable signals into space. Even when you plug in conservative estimates, the result suggests there should be many communicative civilizations in the Milky Way right now. This is the heart of the Fermi Paradox, named for physicist Enrico Fermi, who famously asked, if they are so probable, where is everybody? Our searches, like the decades-long SETI program scanning the skies for artificial radio signals, have heard only silence. Our telescopes have now discovered thousands of exoplanets, some sitting comfortably in the habitable zones of their stars where liquid water could exist. We have found the potential homes but no signs of tenants. So why the great silence? One chilling possibility is the concept of the Great Filter. This is a hypothetical barrier, a step in the evolution of life that is extraordinarily difficult to overcome. It could be that the filter is behind us, meaning the emergence of simple life from non-living chemistry is a cosmic fluke of near impossible odds, and we are the only ones who made it. Or more ominously, the filter could be ahead of us. Perhaps the transition from a technological civilization to a star-faring one is doomed to fail. Every civilization, upon reaching a certain point of development, destroys itself through war, environmental collapse, or some technology we have yet to invent. The silence of the cosmos would then be a cemetery, a warning written in the stars, or maybe we are simply looking for the wrong things or at the wrong time. Civilizations might use communication methods we cannot yet detect, or they might choose to remain hidden. The universe is 13.8 billion years old. We have been listening for less than a century. We could be like ants in a vast forest, unaware of the hikers passing just meters away. Are we alone, the first to awaken, or simply not listening correctly? The answer, for now, remains locked in the quiet between the stars. This profound silence in the cosmos leads our minds back to an even more fundamental emptiness, the very beginning of everything. If the universe is expanding, then running the cosmic film backwards takes us to a single point of infinite density, the Big Bang. But what happened before that? The unsettling truth is that our current laws of physics break down completely at that moment. Time, as we understand it, began with the Big Bang. Asking what came before it might be like asking what is north of the North Pole. The concept of before may simply have no meaning in that context, yet the human mind rebels against this idea. We are wired to think in terms of cause and effect, of a sequence of events. How can something come from nothing? Cosmologists have proposed several breathtaking theories that stretch our imagination to its limits. One leading idea is cosmic inflation. This theory suggests that in the first unimaginably tiny fraction of a second, the universe underwent a period of exponential expansion, far faster than the speed of light, smoothing it out and setting the stage for the Big Bang we talk about. But what triggered inflation? Some models suggest it arose from a random quantum fluctuation in a pre-existing, timeless state, a foaming sea of potential where the concepts of before and after dissolve. Another captivating idea is the cyclical universe, or the Big Bounce. This theory proposes that our universe is not the first, but merely the latest in an endless cycle. A previous universe collapses in a big crunch, rebounds, and expands again in a new Big Bang, over and over for eternity. Time would then extend infinitely in both directions, but each cycle would be a separate cosmic epoch, perhaps with different physical laws. Then there is the mind-bending concept of the multiverse. In this view, our Big Bang was not a unique beginning, but a local event. Our entire observable universe is just one bubble in a vast, eternal cosmic froth, a single note in an infinite symphony of universes, each with its own laws and constants. In such a framework, the question of what happened before our Big Bang transforms. It becomes a question of what is happening in the wider multiverse, a realm forever beyond our observational reach. These are not just scientific speculations, they are philosophical frontiers. They force us to confront the limits of our language and our intuition. We are trying to describe the indescribable with tools forged in a world that began only 13.8 billion years ago. The quest to understand our ultimate origin may be the greatest mystery of all, one that humbles us by revealing how much of reality might exist just beyond the edge of our comprehension. Our current physics paints a terrifyingly simple picture of a black hole. Imagine crushing the mass of our sun down into a sphere just 6 kilometers across, or squeezing the entire Earth into the size of a marble. The gravitational pull at its surface becomes so intense that nothing, not even light, can escape. This point of no return is called the event horizon, a one-way membrane shrouding the black hole's interior. Beyond that horizon, according to Einstein's theory of general relativity, all matter is crushed into an infinitely dense point, a singularity where space and time as we know them cease to exist. Our equations simply spit out infinities, a clear sign that our understanding has hit a wall. Yet black holes are not completely black. In a stunning theoretical leap, Stephen Hawking showed that due to quantum effects at the very edge of the event horizon, black holes can slowly evaporate, emitting a faint whisper of particles now known as Hawking radiation. This discovery created one of the most profound paradoxes in modern science, the information paradox. In the quantum world, information is never truly destroyed. If you burn a book, in principle, you could collect every atom and photon from the smoke and ashes and reconstruct every word. But what happens to the information of an object that falls into a black hole? General relativity says it is lost forever at the singularity. Hawking radiation, however, appears to be random thermal noise, carrying no information about what fell in. If the black hole eventually evaporates away, that information would be erased from the universe, violating a core tenet of quantum mechanics. This is not a minor puzzle, it is a fundamental conflict about how reality works. Does the information get scrambled onto the event horizon's surface like a cosmic hologram? Is it somehow encoded in the Hawking radiation after all? Or is it preserved in some way we cannot yet conceive? Resolving this paradox is seen as a crucial step toward a deeper truth. The true heart of the mystery, however, lies deeper still at the singularity itself. This is where the two great pillars of 20th century physics, Einstein's graceful theory of gravity and the bizarre rules of quantum mechanics, meet and collapse. We need a theory of quantum gravity to tell us what truly happens there. Is it truly a point of infinite density, or does some new physics, like a fabric of space-time woven from tiny loops or strings, prevent that infinite collapse? Our first direct images of a black hole's shadow, captured by the Event Horizon Telescope, are monumental achievements. They confirm the predictions of general relativity in extreme environments. But they are pictures of the black hole's silhouette, its dark heart still hidden. To peer beyond the event horizon to understand the singularity, we require a new kind of vision, a theory that marries the vast cosmic scale with the subatomic quantum world. Until we have that unified theory, the black hole remains the ultimate cosmic vault, guarding its secrets behind an impenetrable wall of darkness. The paradoxes of black holes force us to question the very nature of reality, and that questioning inevitably leads us to a concept that captivates the human imagination like no other. Is time travel possible? The surprising answer from modern physics is not a simple no. According to Albert Einstein's theory of general relativity, time is not a universal, rigid backdrop. It is a flexible dimension woven together with space into a four-dimensional fabric that can be warped and curved by mass and energy. This bending of space-time is what we feel as gravity. And within the mathematics of this elegant theory, pathways that could, in principle, allow travel into the past do appear. They are called closed time-like curves. Think of space-time not as a straight highway from past to future, but as a vast, flexible landscape. A closed time-like curve would be a path through that landscape that loops back on itself, bringing a traveler back to an earlier point in both space and time. One proposed mechanism for creating such a path is a wormhole, often visualized as a tunnel or shortcut connecting two distant points in space-time. If one end of a wormhole could be moved at near light speed or placed near an intense gravitational field, time would pass more slowly for that end relative to the other. This would create a time difference between the two mouths. Walking through the tunnel in one direction could then send you not just to another location, but to another time. The equations allow for it, but here we immediately encounter the infamous grandfather paradox. What if you used such a time machine to go back and prevent your own grandfather from meeting your grandmother? If you succeeded, you would never be born, which means you could never have gone back in time to stop the meeting in the first place. It is a logical contradiction that seems to make backward time travel impossible. Physics offers a few ways to potentially resolve this. The Novikov self-consistency principle suggests the universe simply would not allow the paradox to happen. Any action you took in the past was always part of history. You might intend to change things, but some coincidence or failure would always prevent you from creating an inconsistency. Your trip back was always part of the timeline, a closed loop with no beginning. A more radical solution comes from the many worlds interpretation of quantum mechanics. In this view, every quantum event spawns new, branching universes. If you traveled to the past, you would not be entering your own past, but branching off into a new, parallel timeline the moment you arrived. In that new universe, you could alter events without creating a paradox in your original home timeline. But even if the math permits it and the paradoxes can be sidestepped, the practical barriers are almost comically immense. To stabilize a wormhole against instant collapse, you would need a form of matter with negative energy density, something exotic that we have never seen in nature. The energy requirements to warp spacetime on such a scale are beyond astronomical, perhaps requiring the mass energy of an entire star. Furthermore, many physicists suspect that the wild quantum fluctuations that would occur at the heart of a time machine would destroy it before it could be used, a concept called quantum instability. So is time travel into the past truly forbidden by the laws of physics, or is it just unimaginably difficult? The debate continues. For now, the cosmos seems to protect its chronological order with a series of cosmic locks, from paradoxes to energy requirements we cannot meet. Time may be flexible, but the past appears to be guarded by the universe itself, a story already written in a book we can read but never edit. While time travel remains a tantalizing puzzle of causality, the universe itself is on an irreversible journey toward its own final destiny. The ultimate fate of everything we see, from the smallest atom to the largest galaxy cluster, hinges on a cosmic tug of war between two invisible opponents, the relentless pull of gravity and the mysterious push of dark energy. The outcome of this battle is not yet decided, and the possible endings read like chapters from the most epic science fiction, each more profound and humbling than the last. The most widely accepted scenario, based on our current observations of an accelerating expansion, is known as the Big Freeze or heat death. Imagine the universe as a cup of steaming coffee left alone in a vast, cold room. Over an almost incomprehensible timescale, trillions upon trillions of years, all the energy gradients that power the cosmos will slowly even out. Stars will exhaust their nuclear fuel and burn out. Black holes will, over eons, evaporate via Hawking radiation. Galaxies will drift apart, their lights fading as the space between them stretches into an endless, ever colder void. The universe will approach a state of maximum entropy where no more work can be done, no stars can form, and no processes can occur. It will be a static, dark, and profoundly lonely sea of near absolute zero temperature, with particles so spread out they may never interact again. This is not a dramatic explosion, but a slow, quiet fading of all light and life. But dark energy, the force driving this expansion, holds more unsettling possibilities. What if its repulsive strength is not constant but grows stronger over time? This leads to the most violent cosmic finale, the Big Rip. In this scenario, dark energy's push becomes so dominant that it overwhelms every force that holds things together. First, galaxy clusters would be torn apart, then individual galaxies. As the end approaches, the gravitational grip holding stars within galaxies would fail. Next, planetary systems would be shredded. In the final, terrifying moments, the forces holding atoms themselves together, the very bonds between nuclei and electrons, would be overcome. In an instant, every last bit of matter in the universe would be violently dissociated into its most fundamental, non-interacting particles. The fabric of space-time itself could be torn apart. The universe would end not with a whimper, but with a catastrophic, fundamental unraveling of reality. There is, however, a classic alternative that offers a sense of cyclical renewal, the Big Crunch. This was the favored model before the discovery of dark energy. If the density of matter in the universe were high enough, gravity would eventually win. The expansion would slow, halt, and reverse, pulling all of creation back together in a mirror image of the Big Bang. Galaxies would rush toward each other, the cosmic background radiation would blue shift into a searing heat, and the entire universe would collapse into an ultra-hot, ultra-dense singularity. This end could be a true finale, or it could be a rebirth. Some theories suggest a big crunch could trigger a new Big Bang, leading to an endless cycle of cosmic expansion and contraction, a series of universes with no beginning and no end. Each cycle might have slightly different physical constants, making our universe just one iteration in an eternal sequence. So which of these fates awaits us? The terrifying and beautiful truth is that we do not know because we still do not understand the true nature of dark energy. Is it a constant force, as Einstein once proposed, ensuring a long, cold Big Freeze? Or is it a dynamic field that could decay or intensify, leading to a rip or even a reversal into a crunch? Our measurements are still too imprecise to say for certain. The timescales involved are beyond human comprehension, stretching over hundreds of billions, even trillions of years. Civilizations, stars, and even protons may decay long before the final act. Yet, by asking this question, we are attempting to read the last page of a cosmic story that has only just begun. The uncertainty is a reminder that we are witnessing only the briefest, most vibrant moment in a saga whose final chapters are written in a language we are still struggling to decipher. The universe's final fate may be written in the slow march of dark energy, but right now, our skies are being bombarded by messengers carrying unimaginable violence. These are cosmic rays, not rays of light, but atomic nuclei stripped of their electrons and hurled across the cosmos at nearly the speed of light. Most are low-energy protons from our sun or other nearby stars. But a tiny fraction are something else entirely, ultra-high-energy cosmic rays. A single one of these subatomic particles can carry the kinetic energy of a professionally thrown baseball, all packed into a proton or atomic nucleus smaller than an atom. This is more energy than the most powerful particle accelerator on Earth, the Large Hadron Collider, can ever produce. They are the fastest, most energetic things we know of in the universe. When one of these rare projectiles slams into the top of our atmosphere, it creates a spectacular air shower, a cascade of billions of secondary particles that rain down over an area the size of a city. We detect them not by seeing the primary particle itself, but by capturing this expansive secondary fallout with vast arrays of sensors spread across miles of desert, like the Pierre Auger Observatory in Argentina. The detection is the easy part. The mystery is where they come from. Tracing a charged particle back to its source is a cosmic nightmare. These rays are deflected by the weak but pervasive magnetic fields that thread through interstellar and intergalactic space. Imagine trying to trace the path of a bullet by only watching the splinters it creates after ricocheting off a forest of invisible trees. By the time an ultra-high energy cosmic ray reaches us, its original direction has been completely scrambled. We are left staring at the splinters, trying to guess the shooter's location. The sheer energy these particles carry provides the only clue. To accelerate a proton to such insane speeds requires cosmic engines of almost unimaginable power. The usual suspects are the most violent events in the universe: active galactic nuclei, where supermassive black holes devour matter and blast out jets of plasma traveling at relativistic speeds, could be natural particle accelerators on a galactic scale. The catastrophic mergers of neutron stars, which produce gamma-ray bursts, might also be capable of such feats. Yet, when we look in the rough direction some of these rays seem to come from, we do not always find a suitably monstrous event staring back at us. There is no obvious smoking gun in the sky. This has led to more exotic theories. Could they be the decay products of super-heavy, as yet undiscovered particles left over from the Big Bang? Or signatures of defects in the very fabric of space-time? The puzzle is compounded by something called the GZK cutoff. At such extreme energies, a cosmic ray proton should interact with the cosmic microwave background radiation, the leftover glow from the Big Bang, and lose energy over very long distances. This means ultra-high energy cosmic rays cannot come from too far away, or they would have slowed down. Their sources must be within our local cosmic neighborhood, a few 100 million light-years at most. But within that relatively nearby volume of space, we see no consistent, obvious factories producing them. They arrive seemingly at random from random parts of the sky. Each detection is like a cryptic postcard from a hidden cosmic monster, sent without a return address. We are left with the unsettling realization that something profoundly powerful and utterly mysterious is operating relatively close to our galactic home, flinging atomic bullets at us with forces we cannot replicate, and we have no idea what it is. These cosmic bullets are not the only strange signals raining down from the dark. In 2007, astronomers sifting through old radio telescope data found something that defied explanation, a spike of intense energy so brief it was almost missed. Lasting just a few thousandths of a second, this flash packed more energy than our sun emits in 80 years, all focused into the radio part of the spectrum. They named it a fast radio burst. For years, it was a solitary cosmic oddity, a mystery that some dismissed as a glitch. Then we found another and another. Today, we have catalogued hundreds of these events, and each detection deepens the puzzle. Fast radio bursts are the universe's most powerful and most enigmatic flashes. They arrive without warning from galaxies billions of light-years away, often traversing half the observable universe to reach our telescopes. In that fleeting millisecond, they outshine entire galaxies in radio light. The most baffling part is their variety. Most are one-off events, a single, spectacular shout in the cosmic dark, but a growing number are repeaters, sending out multiple bursts from the same patch of sky, sometimes in predictable patterns, sometimes at random. This tells us that whatever causes them is not always destroyed in the process. It can happen again and again. So what cosmic engine can produce such staggering, focused energy in an instant and then, in some cases, do it over and over? The prime suspect is a magnetar, a type of neutron star with a magnetic field so intense it defies comprehension. A magnetar's magnetic field is a quadrillion times stronger than Earth's, powerful enough to distort the shape of atoms from thousands of kilometers away. Theorists suggest that a starquake on the surface of such a monster, a sudden cracking of its rigid crust under immense magnetic stress, could release a cataclysmic blast of energy in the form of a radio burst. We have even detected an extremely powerful radio burst from a known magnetar within our own galaxy, providing a tantalizing piece of evidence that at least some FRBs come from these magnetic beasts. Yet, the extreme distances of most bursts mean the source must be unbelievably energetic, pushing even a magnetar's limits. Other theories point to the most violent mergers imaginable. When two neutron stars spiral together and collide, they create a black hole in a maelstrom of energy. Such an event could potentially produce a single, catastrophic flash as the final magnetic fields are shredded and the remnants are swallowed. This fits the one-off bursts perfectly, but it cannot explain the repeaters. How can you merge twice? This has led scientists to consider even more exotic possibilities. Could it be the explosive evaporation of a primordial black hole, a relic from the Big Bang, or the collapse of a supermassive neutron star into a black hole? Some have even speculated cautiously about artificial origins like power beams from immense alien spacecraft. While this is the least likely explanation, the sheer power and precision of these signals force us to confront how little we know. The truth is, we are still listening in the dark. New telescopes like the Canadian Chime Array are now catching fast radio bursts almost daily, mapping their locations across the cosmos. Each new detection is a clue, but the definitive source remains a ghost. We are left with a simple, haunting fact: across unimaginable gulfs of space, something is turning on a lighthouse of pure radio energy for a single millisecond, and we have no idea who or what is flicking the switch. The sheer violence that creates a fast radio burst is born from one of the most extreme objects in the universe, a cosmic corpse so dense it defies all earthly logic. When a massive star explodes in a supernova, its core collapses under its own unimaginable weight. If that core is between about 1.4 and 3 times the mass of our Sun, it does not become a black hole. Instead, the force of the collapse crushes protons and electrons together, fusing them into neutrons. The result is a neutron star, a city-sized object with the mass of a star. To grasp this density, imagine taking every single person on Earth and compressing them into a single sugar cube. That cube would weigh over 1 billion tons. A single teaspoon of neutron star material would weigh as much as a mountain. We know they exist. We have detected their rapid spins as pulsars and felt the space-time ripples when two of them collide. But a fundamental mystery remains: what lies beneath that crushing surface? What is inside a neutron star? The surface is a blistering hot crust of iron nuclei locked in a rigid lattice, but as you go deeper, the pressure becomes so immense that atomic nuclei dissolve. You enter an ocean of pure neutrons, a quantum fluid so dense it behaves like a single, gigantic atomic nucleus. Yet even this description is likely an oversimplification. The true nature of matter at these extremes is described by something physicists call the equation of state. This is not a single equation, but a family of theories that attempt to describe how matter behaves when squeezed to densities millions of times greater than an atomic nucleus. It is the ultimate stress test for the laws of physics. Different equations of state predict wildly different interiors. One possibility is that the neutrons remain mostly intact, flowing like a superfluid without any friction deep within the star. Another, more exotic idea is that the neutrons themselves break apart under the pressure. their constituent particles, quarks, might be freed from their confinement, creating a soup of up and down quarks swirling in a new state of matter called quark matter. And there is an even stranger proposal, the idea of strange matter. This theory suggests that at these densities, the most stable form of matter might not be made of the familiar up and down quarks, but would include a heavier, stranger type of quark. If true, a neutron star could have a core of this strange matter, a substance more stable than anything else in the universe. A fragment of it, a strangelet, could theoretically convert any normal matter it touches into more strange matter. We are probing these possibilities not by visiting a neutron star, but by listening to them. Sometimes a pulsar's incredibly regular spin will suddenly speed up in a tiny event called a glitch. This is thought to be a starquake, a sudden cracking of the rigid crust as the spinning star slows over millennia. The way the star vibrates and recovers from this quake tells us about the sloshing, frictionless fluids inside, helping us rule out certain equations of state. Even more revealing are the collisions. When two neutron stars spiral together and merge, they send powerful ripples through space-time gravitational waves that we can now detect. The shape of these waves encodes information about how stiff or squishy the stars are. A softer, more compressible star will deform more easily as they orbit, leaving a different fingerprint in the gravitational wave signal than a harder, more rigid one. Each merger we detect is like a cosmic laboratory experiment, crushing matter to limits we can never achieve on Earth and broadcasting the results across the universe. So while we may never see inside a neutron star directly, we are learning to read its secrets in the tremors of its crust and the echoes of its most violent collisions, slowly piecing together the recipe for the universe's most extreme matter. The extreme matter within a neutron star represents a frontier of physics, but a far more personal mystery unfolded in the warm, shallow waters of our own planet billions of years ago. How did inert chemistry cross the threshold into life? We know the basic ingredients were present on the young Earth: water, organic molecules, and energy from lightning, volcanoes, and sunlight. The leap from that primordial soup to the first living, reproducing cell is arguably the greatest unsolved puzzle in biology. The leading idea is abiogenesis, life arising from non-life through natural chemical processes. One compelling stage for this drama is deep-sea hydrothermal vents. These are not volcanoes, but cracks in the ocean floor where mineral-rich, superheated water gushes into the cold sea. They form towering chimneys with a honeycomb of microscopic pores. Inside these rocky chambers, a constant flow of chemicals and a steep temperature gradient could have acted as a natural laboratory, concentrating simple molecules and providing the energy to forge them into more complex building blocks like amino acids and lipids. The pores themselves could have served as the first protective cells, keeping these precious compounds together long enough for the next critical step: self-replication. This is the true heart of the mystery. We can make the building blocks, but how did they assemble into a molecule that could copy itself? The modern world runs on DNA, but DNA is too complex to have been the first replicator. It requires proteins to function, and proteins require DNA to be built. It is a chicken and egg paradox 4 billion years old. Many scientists now believe the answer was RNA, a simpler cousin of DNA. RNA can store genetic information like DNA, but it can also act as an enzyme, catalyzing chemical reactions, including potentially copying itself. The discovery of ribozymes, RNA molecules that can cut and join other RNAs, gave this RNA world hypothesis powerful support. Perhaps in those warm undersea pores, a lucky RNA molecule emerged that could make rough copies of itself. From that moment, natural selection could begin, even before life as we define it truly started. Yet, despite elegant lab experiments that have recreated many of these steps, no one has ever built a self-replicating system from scratch in a test tube. The gap between promising chemistry and a living cell remains vast. This leads to an alternative, though not mutually exclusive, idea, panspermia. Could the seeds of life have hitched a ride to Earth from elsewhere? Comets and asteroids are known to carry amino acids and other organic compounds. It is possible, even likely, that these cosmic delivery trucks supplied some of Earth's raw materials. The more radical proposal is that microbial life itself, perhaps shielded inside rocks blasted off an ancient Mars by an impact, survived the journey and colonized our planet. This would shift the origin problem to another world, but it does not solve it. It simply moves the miracle elsewhere, which brings us to the cosmic implication of this mystery. If life emerged naturally here through processes bound by the laws of chemistry and physics, then given similar conditions, should it not emerge on other worlds as well? The raw ingredients are everywhere. Organic molecules are found in interstellar clouds, on asteroids, and in the atmospheres of other planets. Water flows on Mars' ancient past and erupts on moons like Europa and Enceladus. If the path from chemistry to biology is a probable, even inevitable, outcome given enough time and the right environment, then the universe should be teeming with life. But if Earth's history required a series of incredibly unlikely chemical accidents, a perfect storm of chance events that may never repeat, then we could be a cosmic anomaly. Our ongoing search for life elsewhere is in essence a test of this idea. Every new exoplanet discovered in a habitable zone, every rover analyzing Martian soil, every future probe tasting the plumes of an icy moon is an attempt to run the experiment a second time. Finding even simple microbial life on Mars or Europa would be a universe-shattering discovery, not just because we are not alone, but because it would tell us that abiogenesis is not a fluke. It is a natural part of a universe that, given half a chance, inevitably awakens. Until we find that second example, the origin of our own existence remains a beautiful, solitary question mark in the silent dark. The silence surrounding the origin of life stands in stark contrast to the cosmic certainty of its invisible architect, dark matter. We know it is there, a ghostly presence 5 times more abundant than all the stars and planets we see, sculpting the universe with its silent gravity. Yet after decades of searching, its true identity remains a phantom in the data. The leading candidate for all these years has been a hypothetical particle known as a WIMP, a weakly interacting massive particle. As the name suggests, this would be a heavy particle that rarely interacts with normal matter except through gravity and perhaps the weak nuclear force. It fits the profile perfectly, a massive, stable, and nearly invisible substance that could have clumped together in the early universe, seeding the formation of galaxies. To catch one, scientists have built exquisitely sensitive detectors deep underground, in old mines and beneath mountains, shielded from cosmic rays. These experiments, filled with ultra-pure liquid xenon or other materials, wait for the telltale, minuscule jolt of a dark matter particle bumping into an atomic nucleus. The problem is, after years of operation with sensitivity increasing by orders of magnitude, these detectors have heard nothing but the quiet hum of background radiation. The WIMPs have not shown up. This profound silence has forced physicists to broaden the hunt. Perhaps dark matter is not heavy but incredibly light. Enter the action. A particle so lightweight and feebly interacting it was originally proposed to solve a different puzzle in particle physics. If actions exist in vast numbers, they could collectively make up the dark matter, flowing through the cosmos like a frictionless quantum wave. Experiments are now searching for these elusive particles by looking for their subtle conversion into photons in the presence of powerful magnetic fields. Another, more dramatic possibility is that dark matter is not a sea of particles at all, but a population of ancient black holes forged in the first chaotic second after the Big Bang. These primordial black holes could range in size from a small asteroid to many times the mass of our Sun, drifting unseen through galaxies. While we have not found evidence for them in large numbers, they remain a compelling, if shadowy, candidate. The world's most powerful particle smasher, the Large Hadron Collider, is also on the case. By recreating the energetic conditions of the early universe, physicists hope to see dark matter particles produced in the collisions. Since they would escape the detector unseen, the signature would be an imbalance in momentum, a telling absence pointing to something invisible carrying energy away. So far, no such definitive signal has emerged. This persistent lack of detection has given rise to a radical alternative, one that questions the very need for dark matter. The theory is called modified Newtonian dynamics, or MOND. It proposes that our understanding of gravity, Newton's and even Einstein's laws, breaks down at the extremely low accelerations found at the edges of galaxies. In this view, there is no missing mass. Gravity just works differently on cosmic scales, providing the extra pull that makes outer stars orbit so fast. MOND can explain the rotation curves of many individual galaxies remarkably well, but it struggles mightily with other evidence. It cannot easily account for the bullet cluster where two galaxy clusters collided. Observations show that the mass, mapped by gravitational lensing, has separated from the visible hot gas. This suggests a huge amount of invisible matter sailed right through the collision, exactly what dark matter would do while the gas was slowed. MOND also has difficulty explaining the large-scale structure of the universe and the patterns in the cosmic microwave background without adding some extra components that look suspiciously like, well, dark matter. This is why most cosmologists still hold to the particle model. The evidence for dark matter's gravitational influence is simply too overwhelming, from galaxy rotation to gravitational lensing to the formation of the cosmic web. The current consensus is not that dark matter does not exist, but that it is simply more elusive, more alien than our first guesses. We may be looking for something that interacts with normal matter 1 trillion times more weakly than a neutrino, a ghost that passes through our planet as if it were not there. Or perhaps dark matter lives in a hidden sector of particles with its own forces and interactions, only rarely brushing against our familiar reality. The search has become a testament to scientific perseverance, a hunt for a shadow that shapes the cosmos, a reminder that the universe is under no obligation to be easily understood. That ghostly dark matter may shape the cosmic architecture, but an even more dominant phantom is actively rewriting the universe's future. The discovery that the cosmos is not just expanding, but doing so at an ever-increasing speed, was so shocking it earned the Nobel Prize. For most of the 20th century, astronomers assumed the universe's expansion, born from the Big Bang, was gradually slowing down. The collective gravity of all the galaxies was thought to be pulling on the cosmic fabric, applying a universal brake. To test this, two independent teams in the late 1990s used a specific kind of stellar explosion, a Type 1, a supernova, as a cosmic yardstick. These explosions have a known standard brightness. By measuring how dim they appear from Earth, astronomers can calculate their distance. By also measuring how much their light is stretched or redshifted by the expansion of space, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The results were unequivocal and stunning. The distant, ancient supernova were fainter than expected. This meant they were farther away than they should be if the expansion had been slowing down. The universe's expansion was accelerating. It was as if you threw a ball into the air and watched it not only fail to fall back, but shoot away faster and faster into the sky. Something was overpowering gravity on the largest scales. That something was named dark energy, and it constitutes about 70% of the total energy budget of the cosmos. But what is it? Physicists have two broad and profoundly different explanations. The first is a cosmological constant, an idea Albert Einstein himself proposed and later discarded. This views dark energy as a fixed property of empty space itself, According to quantum physics, a perfect vacuum is not truly empty. It is a seething foam of virtual particles popping in and out of existence. This quantum activity could endow every cubic centimeter of space with a constant, innate energy that exerts a repulsive pressure. In this model, dark energy's strength never changes. It is simply woven into the fabric of reality. As the universe expands and creates more space, more of this repulsive energy comes into being, driving the acceleration ever faster. The second, more dynamic possibility is a field called quintessence. Imagine a new, unseen kind of force field that permeates all of space, but unlike the cosmological constant, its energy density can change over time and vary from place to place. It could be slowly evolving, weakening or strengthening as the cosmos ages. Quintessence could even allow for regions where the acceleration might one day stop or even reverse. The difference between these two ideas is not academic, it is existential. A cosmological constant points toward a specific cold fate, the big freeze we discussed earlier. But a dynamic quintessence could lead to wildly different endings, perhaps even a future where the universe tears itself apart in a big rip much sooner, or one where expansion eventually halts. So how do we tell which is correct? We need to map the history of the universe's expansion with exquisite precision, tracing how the acceleration has changed over billions of years. This is the primary mission of next-generation observatories like the Nancy Grace Roman Space Telescope. By discovering and measuring thousands of the most distant supernovae, and by using other cosmic markers like the distribution of millions of galaxies, Roman will create a detailed movie of the cosmos's expansion. It will look for any subtle variations in the speed of acceleration over cosmic time. If the data shows the strength of dark energy has remained rock solid, the cosmological constant wins. But if it reveals even a tiny wiggle, a hint that the repulsive force was different in the ancient past, it would be a revolution. It would mean dark energy is a dynamic player in the cosmic story, and the ultimate fate of everything is still an open question, written in a language we are just beginning to translate. Dark energy's phantom push forces us to question the nature of reality itself, and that questioning leads to one of the most provocative ideas in modern thought. What if our universe, with all its galaxies, stars, and the very laws of physics, is not the base layer of reality, but an elaborate simulation? This is not science fiction, but a serious argument debated by philosophers and even some prominent technologists. The logic, often called the simulation hypothesis, runs like this. First, assume that at least one advanced civilization, either our own far future descendants or an alien species, will eventually develop computing power so vast it could simulate entire universes, complete with conscious beings inside them. Second, if such a civilization runs even a modest number of these ancestor simulations for research, entertainment, or historical study, the number of simulated minds would quickly dwarf the number of original biological minds. Therefore, if you are a conscious being, the statistical probability is that you are far more likely to be one of the countless simulated minds than one of the rare original ones. In other words, we are probably living in a simulation. It is a dizzying, almost unsettling piece of cosmic reasoning. But can we move this from a philosophical parlor game into the realm of science? Some physicists argue we might look for potential glitches in the matrix, subtle artifacts that could betray our universe's coded underpinnings. One place to look is at the very small scale. Our reality appears smooth and continuous, but what if it is rendered with a finite resolution like a digital image? In our most powerful particle accelerators, we probe down to scales 1 billion times smaller than an atom, and spacetime still appears smooth. However, some theories of quantum gravity suggest that at the incredibly tiny Planck scale, space itself might be grainy or pixelated. If we ever found evidence of such a fundamental pixelation, it wouldn't prove we are in a simulation, but it would be consistent with the idea of a built-in resolution limit. Another potential signature could be found in the cosmic rays we discussed earlier. If the universe is a simulation, the programmers might take shortcuts to save processing power. They might not simulate every single particle with perfect accuracy, especially for rare, high-energy events. This could introduce subtle statistical anomalies in the distribution of ultra-high-energy cosmic rays, a pattern that defies our standard physical models. Finding such an anomaly would be a profound hint, yet the core debate remains: is this a testable scientific hypothesis or an untestable philosophical one? Critics argue that any glitch we find could simply be explained by new, natural laws of physics, not evidence of a programmer. Furthermore, if the simulation is sophisticated enough, it will be designed to be indistinguishable from base reality, sealing off any hope of detection. Proponents counter that the hypothesis makes a concrete prediction. Our universe should contain observable signatures of computation if we look carefully enough. That makes it, in principle, falsifiable. The true weight of the idea may lie not in a potential discovery, but in the questions it forces us to ask. If we are in a simulation, do the fundamental constants of nature, like the strength of gravity or the mass of an electron, represent lines of code that could be changed? Was our Big Bang simply the start-up of a new simulation run? And what does it mean for concepts like free will, purpose, or the soul? These are not questions physics alone can answer. They blur the line between science, philosophy, and metaphysics, reminding us that our quest to understand the cosmos is also a quest to understand the very nature of our own existence. Whether a profound truth or a fascinating dead end, the simulation hypothesis challenges us to consider that the ultimate mystery may not be out in the distant stars, but in the fundamental code of reality we take for granted every single day. The idea of a simulated reality forces us to confront the very nature of the stage upon which that simulation would run. We talk about space and time as a smooth, continuous fabric, bending and warping under the weight of stars and planets. This is the elegant picture painted by Einstein's general relativity, and it works flawlessly to describe the cosmos on large scales. But when we peer into the heart of an atom, the rules change entirely. The quantum world is a realm of discrete packets, probabilities, and sudden jumps. Particles are not tiny billiard balls, but smeared out clouds of potential, flickering in and out of existence. So which picture is correct? Is the fabric of the universe a smooth sheet, or is it a grainy, digital mosaic? The truth is, we have no idea what space-time actually looks like at its most fundamental level. This is the greatest unsolved conflict in modern physics. Our two most successful theories, general relativity and quantum mechanics, describe reality in mutually exclusive ways, and they break down completely when forced to confront each other. To reconcile them, we need a theory of quantum gravity, a new set of rules for the universe's most basic building blocks. Without it, we cannot understand the first moments of the Big Bang or the crushing depths of a black hole singularity. One of the most mind-bending proposals for the nature of quantum space-time is the concept of quantum foam. Imagine zooming in on the fabric of reality, past atoms, past subatomic particles, down to a scale so unimaginably small it makes a proton look like a galaxy. This is the Planck length, about 10 to the negative 35 meters. At this scale, the smooth geometry of general relativity is expected to dissolve. Instead, space-time itself would become a turbulent, frothing sea. Tiny wormholes could blink in and out of existence. Microscopic black holes could form and evaporate in an instant. The very concepts of before and after lose their meaning in this chaotic, probabilistic foam. It is a place where the universe is constantly rewriting its own rules, a seething ocean of potential geometries. We cannot see this foam directly, of course. The energy required to probe such tiny distances is far beyond anything our particle colliders can produce. But its theoretical existence highlights the profound weirdness we must embrace to understand the quantum structure of space. To make sense of this, physicists have proposed grand, unifying theories. One of the most famous is string theory. It suggests that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings or membranes. The different vibrational modes of these strings give rise to all the particles and forces we see, like different notes on a guitar string. Crucially, in string theory, space-time itself emerges from the interactions of these strings. It is not a pre-existing stage, but a symphony played by countless microscopic performers. String theory is mathematically beautiful and offers a way to unite all forces, but it comes with a staggering cost. It requires extra dimensions of space curled up so small we cannot perceive them, and it predicts a nearly infinite number of possible universes, making specific, testable predictions extraordinarily difficult. An alternative approach is loop quantum gravity. This theory takes a more direct path, applying the principles of quantum mechanics to the fabric of space-time itself. In this view, space is not continuous but woven from a network of finite loops. Picture the universe as a vast, dynamic spiderweb. The intersections of the threads represent tiny, discrete volumes of space, the smallest possible units, like the pixels on a screen. Time, too, would advance in tiny, indivisible steps. This theory naturally avoids the infinities of singularities, suggesting that the Big Bang was not a true beginning, but a rebound from a previous cosmic contraction. Both theories are monumental intellectual achievements, yet they remain just that, theories. The experimental evidence we need to choose between them, or to discover something entirely different, lies far beyond our current technology. Probing the Planck scale would require a particle accelerator larger than our solar system, so we are left in a fascinating and frustrating position. We have two brilliant but incompatible descriptions of reality, and several breathtaking proposals for how to unite them, yet we lack the crucial data from nature itself. We are like cartographers trying to map a continent we can only see from a distant shore, drawing possible coastlines based on the drift of distant clouds. The true structure of space-time at the quantum level is the ultimate hidden architecture of reality, a blueprint we have yet to decipher. If space-time is a fabric, could it be woven with more threads than we can see? The idea that our universe might have hidden dimensions sounds like pure science fiction, yet it is a serious proposal in theoretical physics. We experience three spatial dimensions: length, width, and height, and one of time. This seems like the complete stage for reality, but what if there are more, dimensions so tiny or so warped that our senses and instruments have simply missed them? This is not a new idea. A century ago, mathematicians Theodore Kaluza and Oskar Klein proposed a bold unification. They showed that if you wrote Einstein's equations of gravity in a hypothetical universe with one extra, curled-up spatial dimension, the equations for electromagnetism naturally emerged. Gravity in 5 dimensions looked like gravity plus light in 4. It was breathtaking, a hint that the forces of nature might just be geometry in a higher dimensional space. The theory faded, but the seed was planted. Today, the leading candidate for a theory of everything, string theory, requires extra dimensions to make its math work consistently. Not just 1, but 6 or 7 additional spatial dimensions, curled up into a complex, microscopic shape at every point in space. To understand this, think of a garden hose. From a distance, it looks like a simple one-dimensional line. But if you were an ant crawling on its surface, you would discover it has a second dimension, curled into a tiny circle around the hose's circumference. Our universe might be like that. At every point you can see, there could be a tiny, 6-dimensional geometric shape, a Calabi-Yau manifold, folded up at the Planck scale, 1 billion trillion times smaller than an atom. All the particles we know, quarks, electrons, photons, could simply be different vibrational modes of tiny strings moving through this higher dimensional geometry. The elegance is profound, but the challenge is immense. If these dimensions are so small, how could we ever detect them? Physicists have devised clever tests. One method looks for missing energy. In powerful particle colliders like the Large Hadron Collider, when particles smash together, energy and momentum must be conserved. But if some of the collision energy were to briefly create a particle that traveled into a hidden dimension before snapping back into our own, that energy would seem to vanish from our detectors. We would see an inexplicable gap in the accounting, a signature of something slipping into the unseen. Another approach tests gravity itself. Newton's law tells us the force of gravity weakens with the square of the distance. But some models suggest that at extremely tiny distances, smaller than a millimeter, gravity could begin to leak into extra dimensions, causing it to fall off faster or behave differently. Exquisitely sensitive experiments are trying to measure the gravitational pull between microscopic masses at these vanishingly small scales, hunting for a deviation from the expected law. Beyond detection, the existence of extra dimensions could solve other cosmic puzzles. Could dark matter simply be ordinary matter from a parallel brane, a membrane floating in a higher dimensional bulk whose gravity leaks into our world but whose light does not? Might the inexplicable weakness of gravity compared to other forces be because it is diluted, spreading its influence through many dimensions while the other forces are confined to our three-dimensional brane? These are speculative but thrilling possibilities. They suggest that the answers to our biggest mysteries might not be found by looking farther out into space, but by looking deeper into the hidden geometry of reality itself. The cosmos may be a vast, multidimensional origami, and we have only just begun to unfold a single corner. The hidden geometry of extra dimensions shapes the universe on scales both unimaginably small and vast, but there was a time when the entire cosmos was shrouded in a featureless, silent fog. For hundreds of millions of years after the Big Bang, the universe was a dark, neutral sea of hydrogen and helium gas. No stars had yet ignited, no galaxies had formed. This was the cosmic dark ages, a profound stillness before the dawn. Then something happened. Something began to tear that primordial fog apart. This event, known as the Epoch of Reionization, was one of the most dramatic transformations in cosmic history. The neutral hydrogen atoms that filled space were being blasted apart, their electrons stripped away, turning the universe from an opaque mist into the transparent void we see today. But what provided the incredible power to illuminate and ionize the entire cosmos? The prime suspects are the universe's first true light sources. One candidate is a hypothesized breed of star so massive and pure it almost defies belief, known as population 3 stars. These would have formed from the pristine hydrogen and helium gas left over from the Big Bang, uncontaminated by heavier elements forged in previous stellar explosions. Without those heavier elements to help the gas cool and fragment, these first stars could have grown to be monsters hundreds of times the mass of our Sun. They would have burned ferociously hot and bright, living short, violent lives before exploding as supernova. Their intense ultraviolet radiation would have been like a cosmic blowtorch, capable of ionizing vast bubbles of hydrogen around them. Yet we have never directly seen one. Another potential power source is the early fury of quasars. These are the dazzling cores of distant galaxies, powered by supermassive black holes greedily devouring matter. As gas spirals into these black holes, it heats to millions of degrees, blasting out radiation that can outshine an entire galaxy. A single, bright quasar could be a beacon of ionizing radiation, clearing the fog for millions of light years around it. But did these quasars form early enough and in sufficient numbers to be the primary driver of reionization? Or was it a collective effort with countless faint, early galaxies, each filled with hot, young stars contributing their own ultraviolet glow? This is the core mystery. We know reionization happened because we can see its fingerprint in the light of the most distant quasars. Their light shows telltale gaps, specific wavelengths absorbed by the last remaining patches of neutral hydrogen, like seeing the shadow of the receding fog. But to identify the architects, we need to look directly at the sources themselves, to peer back to that twilight era when the first lights were switching on. This is the revolutionary mission of the James Webb Space Telescope. With its immense infrared eye, Webb is looking back over 13 billion years to a time just a few 100 million years after the Big Bang. It is searching for those first, faint smudges of light, the earliest galaxies, and perhaps even the elusive population 3 stars. By analyzing their brightness, their colors, and the specific signatures in their light, astronomers hope to measure how much ionizing radiation these infant objects were actually producing. Were they powerful enough and numerous enough to have ripped apart the cosmic fog all on their own? Or does the math still not add up, pointing to a missing source of power? The answer will rewrite the first chapters of our cosmic story, revealing whether the universe was illuminated by the brief, brilliant fury of stellar giants, the focused rage of infant black holes, or the combined whisper of countless stellar nurseries flickering to life in the dark. Those first lights that pierced the cosmic fog were not the only behemoths awakening in the early darkness. At the hearts of many of the earliest galaxies we have found, quasars blaze with impossible ferocity, powered by supermassive black holes weighing billions of times our Sun. Their existence so soon after the Big Bang presents a monumental timing problem. How could something so massive grow so incredibly fast? A black hole forms from the collapse of matter, and it grows by feeding, but even eating at the maximum possible rate. There is a speed limit called the Eddington limit. If a black hole feeds too greedily, the intense radiation from the infalling material actually pushes back, preventing more matter from falling in. At this maximum efficient feast, a black hole would take tens of millions of years to double its mass. To reach 1 billion solar masses within the first billion years of the universe requires not just constant feeding, but a head start. It needs a massive seed. This is the core of the mystery. Where did these cosmic giants plant their roots? One leading theory points to the death of the universe's first stars. Those colossal population 3 stars, hundreds of times the Sun's mass, would have lived fast and died young. Their cores would collapse, leaving behind black hole seeds of perhaps a few dozen to a few hundred solar masses. This is a solid start, but the math is a race against time. Could these stellar remnants gorge on gas fast enough and for long enough to balloon into the supermassive monsters we see so early? For many of the most distant, ancient quasars, the timeline feels impossibly tight. It is like expecting a sapling to grow into a 1,000-year-old redwood in just a few decades. This tension has given rise to a more dramatic origin story: direct collapse. Imagine a massive, pristine cloud of hydrogen gas in the early universe, swirling in a dark halo. Under normal conditions, such a cloud would fragment and spark into many stars. But if conditions were just right, perhaps if the gas was prevented from cooling and splitting apart, the entire cloud could collapse in on itself in a single, catastrophic event, bypassing the star formation stage entirely. This could forge a black hole seed thousands, even hundreds of thousands of times the mass of our Sun, a true giant from birth. With that kind of head start, growing to 1 billion solar masses becomes a much more plausible task. But where is the evidence for these middle ground monsters, the intermediate mass black holes that would be the crucial missing link? We have strong evidence for small stellar mass black holes and for the supermassive ones at galactic centers, but the territory in between, from a few hundred to 100,000 solar masses, has been a ghost town. Recently, faint whispers of their existence have begun to surface. Strange, ultraluminous X-ray sources in nearby galaxies could be intermediate black holes feeding on a captured star. Even more compelling are the odd, low-pitch rumbles in the gravitational wave data. some collisions detected by LIGO and Virgo have produced black holes in a mass range that is difficult to explain from normal stellar collapse, hinting at a possible hierarchical growth through mergers in dense star clusters. The future of this detective story lies in listening more carefully to the echoes of the ancient growth spurt. Next-generation gravitational wave observatories like the space-based LISA mission will be tuned to a lower frequency. They will hear the mergers of massive black holes, the very collisions that would have built up the first supermassive giants over cosmic time. By measuring the masses and rates of these collisions from the early universe, we could finally trace the family tree of these galactic titans. Did they grow slowly and steadily from modest seeds, or were they born as royalty, destined from collapse to rule the centers of galaxies? Their origin is not just a curiosity about black holes, it is a question about how the universe built its first cities of stars and why they look the way they do today. That ancient asymmetry in the early universe, the tiny imbalance that allowed matter to survive, is not just a historical footnote. It is the single most important reason you are here to contemplate it. In the first searing moments after the Big Bang, energy condensed into equal amounts of matter and its mirror opposite, antimatter. For every quark, there was an antiquark. For every electron, a positron. When a particle meets its antiparticle, they annihilate in a flash of pure energy. According to this perfect symmetry, the entire universe should have been a brief, brilliant flash, a sea of radiation with no stars, no planets, and certainly no people. Everything should have cancelled out, but it did not. A vanishingly small fraction of matter, about 1 part in a billion, managed to survive that total annihilation. That leftover debris is everything we see in the cosmos today, from the grandest galaxy to the smallest grain of sand. The monumental question is, why was the universe not perfectly symmetrical? Why was there this tiny, life-giving bias for matter over antimatter? Physicists call this puzzle baryogenesis, the genesis of baryons, the class of particles that includes protons and neutrons. To create a matter-dominated universe from an initially symmetrical state, 3 specific conditions outlined by physicist Andrei Sakharov must have been met. First, the universe must have been out of thermal equilibrium. In a perfectly balanced, smooth soup, any particle excess would just get wiped out. You need a disturbance, a cosmic phase transition, like water suddenly freezing into ice, that pushes the system out of balance and allows a new rule to take hold. Second, there must be processes that violate what is called baryon number conservation. Normally, the total number of baryons minus antibaryons is a constant. You cannot just create more matter from nothing. In the early universe, some unknown process had to break this rule, allowing a net baryon number to be generated from an initial state of 0. Third, and perhaps most crucially, there must be a violation of both charge conjugation and parity symmetry, known as CP violation. This is a deeply subtle concept. Charge conjugation symmetry means the laws of physics should be the same if you swap every particle with its antiparticle. Parity symmetry means the laws should be the same if you view the universe in a mirror, flipping left and right. Individually, these symmetries are broken in some weak nuclear interactions. But for baryogenesis, we need a process that violates the combination of both C and P together. It means that matter and antimatter must behave differently, not just as mirror images, but in a fundamental way that favors one over the other. We have found CP violation in the lab, but it is far too feeble to account for the cosmic scale imbalance we see. In particle accelerators, we watch exotic particles called B mesons and K mesons decay. Their antimatter versions decay at very slightly different rates, proving that nature does have a tiny preference. But the amount of asymmetry we measure is 1,000,000 times too small to explain the existence of all the galaxies. So where is the rest of the CP violation hiding? This is one of the driving forces behind some of the world's most precise and patient experiments. deep underground, physicists are watching for a telltale sign in the behavior of neutrinos, those ghostly particles that barely interact with matter. If neutrinos are their own antiparticles, a property called Majorana particles, and if they exhibit CP violation in their oscillations, they could point to a mechanism that operated in the very early universe. Other experiments are scrutinizing the properties of neutrons, searching for an infinitesimal electric dipole moment, a lopsided distribution of charge that would be a glaring sign of new physics and CP violation beyond our current models. The stakes could not be higher. We are searching for the broken rule that wrote us into existence. Every atom in your body is a testament to a fundamental cosmic unfairness, a bias in the laws of physics so slight it seems like a rounding error, yet without it, reality would be a featureless, eternal glow. Finding the source of this asymmetry is not just about completing a chapter in cosmology, it is about understanding why there is something rather than nothing at all. That cosmic bias for matter gave us a universe filled with something rather than nothing, and within that something we have been listening. On August 15, 1977, a radio telescope at Ohio State University known as the Big Ear was sweeping the sky, part of the ongoing search for extraterrestrial intelligence. The data was printed out on line after line of alphanumeric characters, a monotonous record of cosmic static. The next day, volunteer astronomer Jerry Amon was reviewing the printout when his eye caught a sequence of letters and numbers in the data from the constellation Sagittarius. The signal intensity was coded as numbers 1 through 9 and letters for values 10 and above. What he saw was 6EQUJ5. The letters EQUJ represented values of 10, 16, 21, and 10. One column spiked to a value of 6, but the next column over for just 72 seconds, the signal roared to a value of 30, the letter U, the maximum the system could record. Amon circled the sequence in red pen and wrote a single, powerful word next to it, wow. The wow signal was a narrowband radio blast at exactly 1,420 MHz. A frequency that happens to be forbidden for earthly transmitters because it is a protected band reserved for listening to the universe. It came from a region of space with no known stars or planets at that time. It appeared, blazed with incredible strength for just over a minute, and then vanished, never to be heard again despite dozens of follow-up attempts. Its characteristics are what make it so haunting. A natural cosmic source like a pulsar or a quasar would be broadband, spraying radio waves across many frequencies. The wow signal was focused like a laser beam in the radio spectrum. It also exhibited a telltale rise and fall in intensity over the 72 seconds, exactly what you would expect as the Earth's rotation carried the Big Ear's stationary telescope beam slowly across a fixed point in the sky. This matched the profile of a distant, localized source. For decades, it has stood as the best candidate in history for a potential artificial signal from beyond our solar system, a single, enigmatic shout that seemed to say, "Someone is here." Yet with no repetition, it remains a profound mystery, a ghost in the cosmic machine. Such one-off anomalies torment and tantalize astronomers. Centuries later, a different kind of mystery emerged, this time in the flickering of a single star. In 2015, citizen scientists flagged a star now known as Boyajian star or Tabby's star for its bizarre behavior. Data from the Kepler Space Telescope showed it dimming in dramatic, irregular dips, sometimes by as much as 22%. Stars can dim if a planet passes in front, but the dips were too deep, too chaotic, and too asymmetrical. The internet buzzed with the most exciting possibility, an alien megastructure, a vast swarm of solar collectors built by an advanced civilization, periodically blocking the star's light. Scientists raced to investigate every natural explanation. After years of observation, the leading theory points to a colossal cloud of fine dust, perhaps from the breakup of a moon or a swarm of comets, orbiting the star in a complex, clumpy ring. The dust explanation fits the data well, but the exact origin and nature of this extraordinary dust cloud remains unclear. The megastructure hypothesis, while fading, highlighted a crucial point. When we encounter something truly unprecedented in the cosmos, our minds leap to the most extraordinary possibilities because sometimes the universe is just that strange. These singular events, the WOW signal and Tabby star, represent a fundamental challenge in science. How do you study a phenomenon that refuses to repeat? They are cosmic flashes in the pan, leaving behind just enough evidence to spark our imagination, but not enough to reach a definitive conclusion. They are reminders that for all our mapping and cataloging, the universe is still capable of throwing a curveball, a signal from the dark that we receive loud and clear but may never fully understand. The WOW signal and Tabby star remind us that the cosmos is full of unexplained phenomena, but our most profound limitation remains the sheer, crushing distance between the stars. Even with our fastest rockets, a journey to our nearest stellar neighbor, Proxima Centauri, would take tens of thousands of years. This brings us to a question that feels ripped from the pages of science fiction, but is grounded in real physics. Can we ever achieve warp drive or faster than light travel? The tantalizing answer is that the laws of physics, as we currently understand them, might not forbid it outright, but they place hurdles so high they seem almost insurmountable. The dream hinges on a brilliant manipulation of spacetime itself, not by building a faster engine, but by bending the stage upon which we move. In 1994, physicist Miguel Alcubierre proposed a theoretical model for a warp drive. The concept is breathtakingly elegant. Instead of trying to propel a ship through space at impossible speeds, you would manipulate the fabric of spacetime around the ship. Imagine a surfboard riding a wave. The Alcubierre drive would create a warp bubble. Inside this bubble, space would remain flat and normal. The ship would sit motionless within this pocket of calm. But the spacetime in front of the bubble would be massively contracted, pulled toward the ship, while the spacetime behind the bubble would be drastically expanded, pushing the ship away. In essence, the ship would be carried along on a wave of distorted space, potentially reaching speeds that appear faster than light to an outside observer, while never locally exceeding light speed inside the bubble. This clever trick seems to sidestep Einstein's cosmic speed limit, as it is spacetime itself that is moving, not the object within it. The mathematics of general relativity allows for such a solution. It is not science fantasy, it is a valid, if speculative, outcome of our best theory of gravity. But the moment you move from the elegant equations to practical reality, you hit a wall of staggering challenges. The first and most famous is the need for exotic matter. To warp spacetime in the way Alcubierre described, you would need a form of matter with negative energy density. This is not just rare or heavy, it is something with truly bizarre properties. Normal matter always has positive energy density. It warps spacetime in the way we experience as gravity, creating the attractive curvature that holds planets in orbit. Exotic matter with negative energy would warp spacetime in the opposite way, creating a kind of repulsive gravity or anti-gravity effect. We have never observed such a substance in nature. In laboratory settings, certain quantum effects, like the Casimir effect, demonstrate that regions of space can have negative energy density, but these are microscopic, fleeting phenomena. To sustain a macroscopic warp bubble for a starship, you would need planet-sized quantities of this phantom material, and we have no idea how to produce it, contain it, or even if it can exist in such vast amounts. The energy requirements are equally astronomical. Early calculations suggested you would need the equivalent of converting the entire mass of Jupiter into pure energy to power a modest warp bubble. More recent, refined models have brought that number down dramatically, to perhaps the mass of a small moon or even a large asteroid. While that is an improvement, it is still an amount of energy far beyond any civilization we can envision, equivalent to the total output of our sun for years. Beyond the engineering nightmares, there are deeper, more philosophical problems. A warp drive that allows effective faster-than-light travel would almost certainly violate causality, the principle that cause must precede effect. It could create closed time-like curves, opening the door to all the paradoxes of time travel we discussed earlier. Furthermore, physicists have raised concerns about what would happen at the boundaries of the warp bubble. The space in front of the ship would be filled with a wall of incredibly energetic particles and radiation, collected during the journey and released in a catastrophic burst when the drive disengaged, potentially obliterating your destination star system upon arrival. So where does this leave the dream? For now, warp drive remains firmly in the realm of theoretical possibility, a fascinating footnote in the equations of general relativity that highlights the strange flexibility of spacetime. It is a proof of concept that the universe's rulebook might contain a loophole, but one written in a language we cannot yet read, with materials we cannot find, and requiring an energy budget we cannot fathom. The pursuit is not worthless, however. By studying these extreme solutions, we push our understanding of gravity, quantum field theory, and the fundamental structure of reality. The Alcubierre drive is a torch shone into the darkest corners of theoretical physics, illuminating not a clear path to the stars, but the profound depth of our ignorance and the breathtaking potential of what we have yet to learn. The dream of bending spacetime to our will forces us to confront the most elusive frontier of all, not in the stars but within ourselves. What is consciousness? Is it merely a biological accident, a flickering byproduct of complex neural wiring, or could it be something more fundamental, perhaps even woven into the fabric of the cosmos? This question sits at the strange intersection of neuroscience, philosophy, and astrophysics, and it changes everything about how we imagine life beyond Earth. If consciousness is exclusively a product of carbon-based brains, then alien minds might be rare and somewhat familiar. But if it is something else entirely, the universe could be awake in ways we cannot yet perceive. One radical idea gaining traction is panpsychism. This ancient philosophy, updated with modern physics, suggests that consciousness is a basic property of the universe, like mass or charge. In this view, all matter has some tiny, elemental spark of experience. A single electron would possess an infinitesimal degree of consciousness. In most things, like a rock or a star, these sparks are so simple and unintegrated that they amount to nothing we would recognize as a mind. But in highly complex systems like a human brain, these countless sparks combine and integrate, giving rise to the rich, flowing stream of awareness we know. A related, more formal theory is integrated information theory, or IIT. It proposes that consciousness is not about what a system does, but how it is structured. Any system that has a high degree of integrated information, where the whole is more than the sum of its parts, possesses some level of consciousness. This could apply to a brain, but also, in principle, to other complex, interconnected systems. This leads to a staggering possibility. Could a planet-wide mycorrhizal network of fungi be conscious? Could the swirling, self-organizing patterns in Jupiter's Great Red Spot, if complex enough, have some dim, alien form of experience? Could a sufficiently advanced artificial intelligence, running on silicon rather than synapses, become truly aware? If IIT or panpsychism holds any truth, then consciousness might not be a rare miracle, but a common feature of a complex cosmos. This completely reframes the search for extraterrestrial intelligence. We have been listening for radio signals and looking for techno-signatures, assuming any advanced civilization would build things we can detect. But what if the most advanced intelligence in our galaxy is not a civilization at all? It could be a planetary-scale network of crystalline structures, communicating through subtle vibrations in a moon's crust. It could be a distributed mind within the magnetosphere of a star, thinking in pulses of plasma and magnetic fields over millennia. It could be a cloud of interstellar dust organized by some unknown principle into a vast, slow thought. How would we even begin to recognize such an entity? Our entire concept of communication is built on the assumption of a localized, intentional agent with goals and a language. A stellar consciousness might perceive the universe in terms of gravitational tides and stellar nucleosynthesis, its thoughts unfolding over centuries. Our frantic radio messages would be like the brief, meaningless crackle of static to it. Our most powerful telescopes might be looking directly at such a mind and seeing only natural phenomena. This is the ultimate challenge of contact. We are not just separated by distance, but by the very nature of experience. Searching for a non-biological consciousness would require a new kind of science, one that looks for anomalous complexity, for patterns in nature that encode vast amounts of integrated information for no apparent survival reason. It would mean listening not just for signals, but for the universe's own rhythm, wondering if the silent spaces between the stars are not empty, but deep in thought. The mystery of consciousness, therefore, is not just about us. It is the key to understanding what else might be out there, waiting in forms so alien that to call them life might be the first and greatest misunderstanding. That profound mystery of consciousness, a potential whisper in the cosmic dark, is confined to a tiny, illuminated bubble. Our entire reality, everything we have ever seen or detected, exists within a sphere called the observable universe. Its edge is not a physical wall, but a horizon in time. Light has a finite speed, and the universe has a finite age, 13.8 billion years. This means the most distant light that could possibly have reached us has been traveling for exactly that long. We cannot see anything farther, not because it does not exist, but because its light has not had enough time to cross the vast gulf of expanding space to reach our telescopes. This creates a cosmic prison of information, a bubble roughly 93 billion light-years in diameter, containing perhaps 2 trillion galaxies. And this leads to a staggering question. What lies beyond the cosmological horizon? Is there simply more of the same, an endless continuation of galaxies and voids stretching into infinity? Or does the universe change character in ways we cannot imagine? Our best theories suggest the true cosmos is almost unfathomably larger than our tiny, observable patch. The leading idea is cosmic inflation. In the first fraction of a second after the Big Bang, the universe is thought to have undergone a period of exponential, faster-than-light expansion, smoothing it out and setting its initial conditions. A critical consequence of inflation is that it did not stop everywhere at once. In our region, inflation ended, allowing particles to form and galaxies to coalesce. But in the greater meta-universe, inflation may be eternal, continuing in other regions, constantly spawning new, separate bubble universes. In this picture, our entire observable universe is just one bubble in an endless, frothing sea of inflating space. Each bubble is a self-contained universe, potentially with its own unique laws of physics. Some bubbles might have stronger gravity, making stars burn out in millions of years instead of billions. Others might have no weak nuclear force, preventing the formation of complex atoms. In others, the cosmological constant might be so large that the universe tears itself apart instantly, or so negative that it collapses back on itself immediately. This is the multiverse in its most dramatic form. A cosmic archipelago where the fundamental constants of nature are not universal truths, but local environmental conditions like the climate on an island. We happen to live on an island where the constants allow for atoms, stars, planets, and life. This is called the anthropic principle, the idea that we observe a universe compatible with our existence simply because we could not observe one that is not. But is there any way to test this? Can we ever know what lies beyond our horizon? The answer, frustratingly, is probably no, at least not directly. The space beyond our observable universe is expanding away from us so quickly that the light from those regions will never reach us. They are forever beyond our causal reach, receding into an inaccessible darkness. However, there might be indirect, ghostly evidence. If our bubble universe collided with another bubble in the distant past during the early inflationary phase, the collision could have left an imprint on the cosmic microwave background radiation, a kind of bruise on the oldest light in the sky. Astronomers have searched for such anomalous patterns, but so far, none have been conclusively found. The reality is that the question of what lies beyond may be fundamentally unanswerable by science. It exists in the realm of philosophical speculation, constrained by mathematics but untouchable by experiment. We are like sailors on a raft in an infinite ocean, able to see only to the curve of the horizon, wondering if the sea goes on forever, or if just beyond our sight there are other oceans with different colors and different rules, islands of reality forever separated by an impassable expanse of dark, inflating water. The vast, invisible architecture of the cosmos is not built by gravity alone. Woven through the spaces between stars and galaxies are immense, ghostly structures of pure force. Cosmic magnetism is a quiet, pervasive power shaping the birth of stars and guiding the flow of galactic gas, yet we have almost no idea how it began. These magnetic fields are astonishingly weak, millions of times fainter than a common refrigerator magnet, but they stretch across hundreds of thousands of light years. They exist in the spiral arms of galaxies like our Milky Way. They thread through the colossal voids between galaxy clusters, and they even leave their imprint in the ancient light from the Big Bang. The sheer scale of the phenomenon is the first part of the mystery. How does a force we associate with bar magnets and compass needles come to dominate the architecture of the universe? The leading theory takes us back to the universe's infancy. In the seething plasma of the first moments, quantum fluctuations and violent phase transitions could have generated minuscule seed fields, random wrinkles in the electromagnetic fabric of reality. These would have been unimaginably faint, but they were not zero. Once these seed fields existed, a cosmic engine could take over, the dynamo effect. Picture the swirling, electrically conductive plasma in the disk of a young galaxy. As this vast ocean of charged particles rotates and churns, it can stretch and twist these weak seed fields, amplifying them over hundreds of millions of years, much like a turbine generates power from a small initial current. The dynamo theory is elegant and powerful, explaining how a whisper can become a cosmic shout. But it requires that first whisper to exist. Did those primordial seed fields form in the first second after the Big Bang, or did they arrive later? An alternative story suggests magnetism is a later invention. Perhaps the first stars and galaxies themselves were the architects. The violent outflows from supernova, the powerful jets from active black holes, these cataclysmic events could have sprayed magnetized plasma into intergalactic space, seeding the voids with magnetic fields that later galaxies would inherit and amplify. This would mean magnetism is not a fundamental feature of the cosmos, but a byproduct of its most violent stellar citizens, a cosmic pollution that eventually became essential. The challenge in solving this puzzle is that these fields are incredibly difficult to measure. We cannot simply hold up a compass in intergalactic space. Instead, astronomers rely on subtle clues. They study the polarization of starlight, how its waves are oriented as it passes through magnetized dust. They observe synchrotron radiation, the faint glow emitted by electrons spiraling at near light speed along magnetic field lines. Each observation is like listening for a distant echo in a hurricane, requiring instruments of breathtaking sensitivity. Yet the answer matters profoundly. Magnetic fields are not just cosmic decoration. They regulate the collapse of gas clouds to form new stars, providing a supporting pressure that can slow down gravitational collapse. They channel cosmic rays, guiding these ultra-high energy particles through the galaxy. They influence the structure of spiral arms and the stability of galactic disks. If we do not understand the origin and strength of these fields, our picture of how galaxies live and evolve is fundamentally incomplete. We are left with a universe quietly humming with a force whose birth we cannot see, a silent symphony playing since the dawn of time, its first note forever lost in the noise of creation. While cosmic magnetism hums a quiet, persistent tune, the universe also screams. For a few fleeting seconds, it unleashes the most powerful explosions since the Big Bang itself, events so violent they outshine entire galaxies in pure, furious light. These are gamma-ray bursts, and for decades they were the sky's greatest secret, brief flashes of high-energy radiation picked up by military satellites watching for nuclear tests. Today, we know they come from billions of light-years away, and we have begun to categorize their terrifying origins, though their ultimate engines remain shrouded in mystery. We now recognize two distinct apocalyptic families. The first are the long-duration bursts lasting from 2 seconds to several minutes. These are thought to be the death cries of the most massive stars in the universe. When a star dozens of times heavier than our Sun exhausts its fuel, its core collapses catastrophically, not into a neutron star but directly into a black hole. As the outer layers of the star rain down onto this newborn singularity, a fraction of that infalling material is redirected into two opposing jets, blasted out at over 99.99% the speed of light. These jets, composed of ultra-relativistic particles, drill their way out through the collapsing star. When they finally breach the stellar surface, they interact with the surrounding material, creating the intense flash of gamma rays we see as the burst. The star itself is utterly obliterated in a supernova, or more accurately, a hypernova, hundreds of times brighter than a typical stellar explosion. The second, even more enigmatic type are the short-duration bursts. These last less than 2 seconds, sometimes just a few milliseconds, but they pack a staggering punch in that blink of an eye. The leading suspect for these ultra-fast flashes is the ultimate cosmic collision, the merger of two neutron stars or a neutron star and a black hole. As these incredibly dense objects spiral together over millennia, they finally touch, triggering a cataclysm that rips them apart. In the final milliseconds, a torrent of neutron-rich material is ejected, forging heavy elements like gold and platinum in a process called rapid neutron capture. At the heart of this maelstrom, a new black hole is likely born, again launching relativistic jets that produce the brief, intense gamma-ray signal. In 2017, we witnessed this theory become reality in the most spectacular way. The LIGO and Virgo gravitational wave observatories felt the space-time ripples from a neutron-star merger. Just 2 seconds later, the Fermi and Integral satellites saw a short gamma-ray burst coming from the same patch of sky. This historic event, known as GW170817, was the dawn of multi-messenger astronomy. For the first time, we could hear the collision through gravitational waves and see its fiery aftermath in light across the spectrum, from gamma rays to the glowing kilonova that followed. It confirmed the origin of short bursts and showed us the cosmic forges where the universe's gold is made. Yet, even with these breakthroughs, profound mysteries linger. What is the exact engine that powers these jets? For long bursts, is it always a newborn black hole, or could a rapidly spinning, highly magnetized neutron star, a magnetar, provide the power? For short bursts, does the merger always produce a stable black hole, or could it briefly create a hypermassive neutron star that lasts a few moments before collapsing? The jets themselves are another puzzle. How do they become so focused and energetic? The process likely involves intense magnetic fields wound up by the rapid rotation of the central engine, acting like a cosmic railgun to accelerate matter to such insane speeds. We are now entering a new era of investigation, where every gamma-ray burst alert sends a global network of telescopes, neutrino detectors, and gravitational wave observatories into action. By combining these different messengers, we can piece together a three-dimensional picture of the explosion. Neutrinos, if we can catch them from a burst, would tell us about the nuclear reactions in the stellar core at the moment of collapse. Gravitational waves from a long burst, which we have not yet detected, would reveal the asymmetrical jolt of the collapsing core itself. Each new detection is like receiving a different page from the same catastrophic story. These bursts are more than just distant fireworks. They are the universe's most extreme physics laboratories, probing gravity, matter, and energy under conditions we can never recreate. They are also cosmic lighthouses, their light traveling across billions of years, allowing us to map the distant universe. Solving their final secrets means understanding the final moments of stellar life and the birth cries of black holes, written in the most violent language the cosmos knows. The staggering violence of gamma-ray bursts forces us to confront a deeper, more unsettling cosmic truth. The universe is not just powerful, it is precise. The fundamental constants that govern reality, the strength of gravity, the mass of an electron, the force that binds atomic nuclei, these numbers are not random. They appear to be exquisitely, almost miraculously tuned. If any one of them were altered by even a tiny fraction, the universe as we know it would not exist. Stars would not burn, atoms would not hold together, and life of any conceivable kind would be impossible. This observation, known as the fine-tuning problem, sits at the razor's edge between science and philosophy, asking a question that echoes through the cosmos. Is this perfect balance mere luck or evidence of a deeper design? Consider gravity. If the force of gravity were slightly stronger, stars would burn through their fuel too quickly, collapsing into black holes before life could evolve on any orbiting planets. If it was slightly weaker, matter would never have clumped together to form stars and galaxies in the first place. The universe would be a cold, dark, and eternal fog. Or take the cosmological constant, the energy of empty space that drives the universe's acceleration. Its observed value is astonishingly small. If it were just a little larger, the repulsive force would have torn apart proto-galaxies before they could form. If it were negative, the universe would have collapsed back on itself almost immediately after the Big Bang. The window for a life-permitting universe seems impossibly narrow. This precision has led some to propose the argument from design, suggesting that such a perfect balance points toward an intelligent architect, a cosmic engineer who set the dials just right. It is an ancient intuition that the clockwork perfection of the cosmos implies a clockmaker, yet science offers alternative explanations that do not require a designer, and they are just as mind-bending. The first is the anthropic principle, a simple but profound logical filter. It states that we can only observe a universe that is compatible with our existence as observers. If the constants were different, we would not be here to wonder about them. In this view, there is no mystery to solve. We are simply the inevitable product of a universe that allows for conscious life. The fine-tuning is not a clue, but a prerequisite. A more expansive scientific answer is the multiverse. If our universe is just one bubble in an infinite, eternally inflating meta-universe, then every possible combination of physical constants exists somewhere. In an infinite number of universes, there will be a tiny fraction where the numbers line up perfectly for stars, planets, and life. We, of course, find ourselves in one of those rare habitable bubbles. The fine-tuning is not evidence of design, but of a cosmic lottery with an infinite number of tickets. Our winning ticket just happens to allow us to read the numbers. A third possibility is that we have not yet discovered the deeper theory that explains these constants. Perhaps they are not free parameters to be tuned, but are mathematically necessitated by a more fundamental law of nature, a single, elegant equation from which all forces and particles emerge. In this view, the constants could not be any other way because they are the only logical outcome of the universe's underlying structure. The apparent fine-tuning is an illusion created by our incomplete understanding. Finally, some scientists question the premise itself. Could life, in forms we cannot yet imagine, exist under radically different physical laws? Our definition of life is based on carbon chemistry and liquid water, but that is a sample size of one. Perhaps in a universe with a stronger nuclear force, complex structures could form in the swirling plasmas of stars, or consciousness could arise in the vast, slow magnetic fields of a nebula. If life is more adaptable than we think, then the window for a habitable universe might be much wider and the tuning less fine. This is not a question science can answer with a telescope or an equation alone. It lives in the borderlands where empirical evidence meets metaphysical wonder. The fine-tuning of the cosmos forces a choice of perspective. Do we see a universe crafted with intention, or one born from an infinite game of chance? Is our existence a happy accident in a lonely bubble, or the expected outcome of a deeper yet unseen logic? For now, the constants remain silent, their values a permanent part of our reality, their origin a mystery written into the fabric of every atom. That fine-tuning of the cosmos, the precise balance of forces and constants, is what allowed the first atoms to form from a cooling sea of energy. In the first 3 minutes after the Big Bang, the universe was a seething nuclear furnace, hot and dense enough to fuse protons and neutrons into the lightest atomic nuclei. This brief explosive period is called Big Bang nucleosynthesis, and it is one of the great triumphs of modern cosmology. The calculations, based on the known laws of nuclear physics and the expansion rate of the early universe, predicted that about 25% of the ordinary matter by mass should have ended up as helium-4, with trace amounts of deuterium, helium-3, and a single light metal, lithium-7. For the most part, the predictions are spectacularly accurate. When we look at the oldest, most pristine gas clouds in the universe, the observed abundances of hydrogen, helium, and deuterium match the theoretical calculations almost perfectly. It is a stunning confirmation of our understanding of the universe's first moments, but there is a glaring, persistent exception. The lithium does not add up. The amount of lithium-7 we actually observe in these ancient stars is only about 1/3 of what the theory says should have been forged in the Big Bang. It is not a small error, it is off by a factor of 3. This is the cosmological lithium problem, a quiet but profound crack in our otherwise flawless picture of the infant cosmos. So where did the lithium go, or was it never made in the expected amounts to begin with? One possibility is that our understanding of nuclear physics in those extreme conditions is incomplete. The predicted lithium abundance depends sensitively on the rates of specific nuclear reactions that occurred during that frantic 3-minute window. If certain reaction rates, particularly those involving beryllium-7, which decays into lithium-7, are different than what we measure in Earth-based laboratories, it could resolve the discrepancy. Scientists are constantly refining these measurements, but so far, no adjustment has fully closed the gap. Another line of thought looks not at the birth of lithium, but its potential destruction. Perhaps the lithium was created in the predicted amounts, but was later destroyed inside the very stars we use to measure it. The oldest stars in our galaxy, known as population 2 stars, are our cosmic time capsules. They formed from nearly pure Big Bang material, so their surface composition should reflect primordial abundances. But what if processes in these stars over billions of years have slowly transported surface lithium down into hotter interior layers where it is fused into heavier elements? This kind of stellar mixing could explain the lower observed levels, but models of stellar evolution struggle to produce enough mixing to account for all the missing lithium without contradicting other observations about these stars. The most exciting possibility is that the lithium problem is a sign of new physics at play in the early universe. Could an unknown particle, like a certain type of dark matter, have been present during nucleosynthesis, altering the density or expansion rate at just the right moment to suppress lithium production? Or does it point to something more fundamental, like a slight variation in the forces of nature during that first, unimaginable heat? The lithium problem is a reminder that even our most successful cosmic stories are not yet complete. It is a single, stubborn data point that refuses to fit, a whisper from the first 3 minutes that we have not yet fully understood. Solving it may require not just better astrophysics, but a glimpse into physics beyond our current standard model, hidden in the faint signature of a light metal born at the dawn of time. These ancient whispers of lithium formed in a universe already filled with planets, but not all worlds are blessed with a sun. Drifting through the interstellar void, untethered from any star, are the galaxy's loneliest nomads, rogue planets. Picture a world like Jupiter or Earth, but in perpetual night, traveling a solitary path through the cold, empty spaces between the stars. These are not mere asteroids or comets, but full-fledged planets, some likely larger than Jupiter, others possibly rocky worlds like our own, cast adrift from their stellar homes or born in the dark. They become wanderers through two primary, dramatic paths. The most common origin is likely ejection. In the chaotic early days of a young solar system, as giant planets jostle for position, gravitational slingshot interactions can fling a smaller world entirely out of the system, sending it careening into the galactic abyss. It is a cosmic game of billiards with planetary stakes. The other possibility is even more isolated. A planet could form all on its own. A small, dense knot within a collapsing gas cloud might have just enough mass to become a planet, but not enough to ignite into a star. This lonely genesis would create a planet that never knew the warmth of a sun, a world born into darkness. The true mystery is not their existence, but their staggering abundance. How many of these dark wanderers are there? Estimates from gravitational microlensing surveys, where a rogue planet's gravity briefly bends and magnifies the light of a distant star, suggest a number that is almost incomprehensible. There could be trillions of them in the Milky Way alone, outnumbering stars by a factor of hundreds or even thousands. For every star you see in the night sky, there could be 100 cold, dark planets silently drifting in the blackness around it. Our galaxy may be less a collection of solar systems and more a vast sea of orphaned worlds. Detecting them is a monumental challenge. Without a star to illuminate them, they are virtually invisible in ordinary light. Microlensing is our most powerful tool, but it is a fleeting and rare event, a single alignment that lasts only hours or days. Other methods include looking for the faint, residual heat glow from a young, still warm rogue planet in infrared light, or spotting one silhouetted against a bright nebula. Each detection is a triumph of patience and precision, a glimpse of a ghost. Yet, the most profound question about these dark worlds is not how we find them, but what might exist on them. A rogue planet devoid of stellar warmth is not necessarily a dead, frozen rock. Tidal forces from a large moon or heat from radioactive elements in its core could maintain a vast global ocean of liquid water beneath a thick crust of ice. In the eternal darkness of such a subsurface sea, bathed in geothermal warmth, the chemistry for life could persist for billions of years, completely isolated from the rest of the galaxy. Life on a rogue planet would evolve in a world without day or night, without seasons, its only energy coming from the planet's own internal heat. It is a haunting possibility that the most common abode for life in the universe might not be a planet orbiting a friendly sun, but a lost world wandering the lightless deep, carrying its own private, inner ocean through the eternal cold. This cosmic orphan, drifting through the interstellar night, is a reminder that our most profound questions often lie in the gaps between our grandest theories. Our understanding of the universe is built on two pillars, each magnificent in its own domain, yet they speak completely different languages and cannot be reconciled. On one hand, we have quantum mechanics, the rulebook for the impossibly small. It describes a world of probability clouds, particles that are also waves, and spooky connections across vast distances. It is bizarre, counterintuitive, and unbelievably accurate for everything from the chemistry of life to the transistors in your phone. On the other hand, we have general relativity, Einstein's masterpiece that describes gravity as the curvature of spacetime by mass and energy. It gives us black holes, the expanding cosmos, and the bending of light around galaxies. It is elegant, geometric, and perfectly describes the universe on its largest scales. The problem is, these two theories are mutually exclusive. They break down completely when forced to confront each other, such as at the center of a black hole or the very first instant of the Big Bang. To understand the universe's most extreme moments, we need a single, unified framework, a theory of everything. This is not just an academic exercise, it is a quest for the fundamental language of reality itself. The two most prominent contenders in this epic struggle are string theory and loop quantum gravity, and they could not be more different in their approach. String theory proposes that the fundamental ingredients of the cosmos are not point-like particles, but unimaginably tiny, vibrating strings. Just as different vibrations on a violin string produce different musical notes, the different vibrational modes of these strings give rise to all the particles and forces we see, from electrons to photons to the carriers of gravity. It is a breathtakingly beautiful idea, a cosmic symphony where every particle is a note. But to make the math work, string theory requires extra dimensions of space, tiny, curled-up shapes at every point far smaller than an atom. The theory naturally includes gravity and holds the promise of unifying all forces, but it comes with a cost. It predicts a nearly infinite number of possible universes, making specific, testable predictions extraordinarily difficult. Loop quantum gravity takes a more direct, almost architectural view. Instead of adding new objects like strings, it applies the rules of quantum mechanics directly to the fabric of spacetime itself. In this theory, space is not smooth and continuous. It is woven from a network of finite, indivisible loops. Picture the universe as a dynamic, evolving spiderweb. The intersections of the threads represent the tiniest possible volumes of space, like the pixels on a screen, and time advances in tiny, discrete ticks. This theory naturally avoids the infinities of singularities, suggesting the Big Bang may have been a bounce from a previous cosmic phase. Both theories are monumental intellectual achievements, representing decades of work by some of the brightest minds on the planet. Yet, for all their mathematical elegance, they share a profound and frustrating limitation: a lack of experimental predictions we can test with our current technology. To probe the scales where these theories operate, the Planck scale, we would need a particle accelerator larger than our solar system. We are, for now, theorists trying to map a continent we can only see from a distant shore, drawing possible coastlines based on the drift of distant clouds. The pursuit may seem abstract, but the stakes are nothing less than the nature of reality. A successful unification would tell us what spacetime is made of at its core. It would reveal what truly happens at the singularity of a black hole and what sparked the Big Bang itself. It would bridge the vast chasm between the quantum weirdness of the atom and the graceful curvature of the cosmos, giving us a single story that explains everything from the spin of an electron to the fate of galaxies. Until we find that story or build the tools to test these breathtaking ideas, the universe guards its ultimate secrets in the silent space between two brilliant but conflicting descriptions of itself. Our quest for a single theory to explain reality inevitably leads us to a question that science alone cannot answer. We have mapped the birth of stars and the pull of dark matter, but these are descriptions of how the cosmos functions. They tell us nothing about why any of it is here in the first place. Does the universe possess an inherent purpose, a grand design written into its laws? Or is it a magnificent but ultimately meaningless accident? This is where our journey shifts from the telescopes of cosmology to the introspection of philosophy. From a purely physical standpoint, the universe appears to be a vast, unconscious machine, governed by mathematical rules that play out with no goal or intention. Stars burn because nuclear fusion is a consequence of physics, not because they are meant to light the way for life. Galaxies collide and black holes devour matter because gravity dictates their motion. In this view, purpose is a human invention, a story we tell ourselves to find comfort in the indifferent silence. The cosmos simply is. Any meaning we find is something we project onto it, like seeing faces in the clouds. Our existence, then, is a fleeting, beautiful anomaly in an endless void that neither knows nor cares that we are here. Yet there is a counterpoint that emerges from the data itself. Look at the arc of cosmic history from the Big Bang to today. Over 13.8 billion years, the universe has evolved from a featureless soup of particles toward ever greater complexity and structure. Hydrogen atoms coalesced into stars, stars forged heavier elements in their cores, and those elements assembled into planets and, on at least one world, into living, thinking beings. This trajectory from simplicity to complexity and ultimately to consciousness is a measurable fact. Could the emergence of observers be a significant, even defining feature of the cosmos? Some thinkers propose the participatory anthropic principle, suggesting that the universe requires conscious observers to bring it into being in a meaningful sense. In quantum mechanics, an observation can determine the state of a particle. Could the cosmos, in some profound way, need minds to complete it? This is not a scientific claim, but a philosophical wonder born from scientific discovery. Different traditions offer their own answers. Many religious and spiritual frameworks see the universe as the deliberate creation of a divine intelligence, with purpose woven into its fabric. Humanity, or consciousness itself, might play a role in a cosmic plan. Secular humanism finds purpose not in a preordained script, but in the values we create and the future we build with our brief moment of awareness. The universe's meaning, in this light, is the meaning we courageously choose to make. Perhaps the most humbling perspective is that both answers might be true in their own realms. Science reveals a universe of breathtaking order and emergent beauty, one that allows for creatures who can ask why. Philosophy and spirituality explore the inner experience of being such a creature within that order. The purpose of the universe may be an unanswerable question, but the act of asking it is itself a profound testament to what the universe has produced. We are the cosmos become self-aware, staring back at itself and wondering what it all means. In that wondering, we may not find a final answer, but we discover something equally astonishing, our own capacity for awe, for curiosity, and for the creation of meaning in the face of the infinite dark. Perhaps the greatest discovery in our cosmic journey is not an answer, but a pattern. Every time we peel back a layer of the universe, we find not a final, solid floor, but another, more intricate layer beneath it. This leads us to the final and perhaps most humbling question on our list. Will we ever understand everything? Is there a fundamental limit to human knowledge, a boundary beyond which our minds, our tools, or the very laws of logic cannot take us? The pursuit of a final theory, a complete set of equations that explain all of reality, might be chasing a mirage. A profound hint comes not from physics, but from mathematics, from the work of Kurt Gödel. In the 1930s, Gödel proved his incompleteness theorems. In simple terms, he showed that in any sufficiently complex mathematical system, there will always be true statements that cannot be proven from within the system itself. The system is either incomplete or inconsistent. You cannot have a single, self-contained set of rules that proves every truth about itself. If mathematics, the language of the universe, is inherently incomplete, what does that imply for physics? It suggests that any final theory of everything we construct might also be incomplete. There could be phenomena, facts about the cosmos that are true and real, but that the theory itself is fundamentally incapable of predicting or explaining. We might build a perfect, self-consistent model of 99.9% of reality, but there will always be truths that lie outside its grasp, shimmering just beyond the edge of comprehension. Our knowledge may be bounded by the very tools we use to acquire it. Consider the scale of the cosmos. The observable universe is a prison of information, limited by the finite speed of light and the age of the universe. We can never know what lies beyond our cosmological horizon. The multiverse, if it exists, is by definition unobservable. We are like goldfish in a pond, trying to deduce the nature of the ocean from the ripples on our surface. Then there is the quantum world, where the act of observation fundamentally alters what is being observed. At the most basic level of reality, there is a built-in uncertainty, a fuzziness that prevents us from knowing everything with perfect precision. You can know where a particle is or how fast it is moving, but not both at once with absolute certainty. This is not a limitation of our instruments, it is a law of nature. Finally, we must confront the structure of our own brains. We are evolved primates, our cognition shaped by natural selection to solve problems of survival on an African savanna. Is a brain built to recognize predators and find ripe fruit truly equipped to comprehend the 11-dimensional geometry of string theory or the true nature of a singularity? Our intuition is forged in a world of medium-sized objects moving at slow speeds. The deeper truths of the cosmos are profoundly counterintuitive. They feel alien because in a very real sense they are. Yet here is the beautiful paradox. This apparent limit is not a dead end, it is an endless frontier. Each mystery we solve does not close a book, it opens a library. Understanding the nuclear fusion in stars revealed the mystery of the missing solar neutrinos. Discovering the expansion of the universe revealed the deeper mysteries of dark energy and the cosmic horizon. The journey of science is not a march toward a finish line, but an endless ascent. With each step upward, the horizon recedes, revealing new, more breathtaking vistas. The purpose is not to arrive at an end, but to continue the climb. The 30 questions we have explored today are not failures of science, they are its greatest successes. They are the signposts at the edge of the known, pointing into the magnificent dark. They remind us that the universe is not a puzzle to be solved, but a story to be continued, a story in which we, for a brief and shining moment, have the privilege of being both the audience and the authors. Our understanding may always be incomplete, but our wonder need never be. That endless frontier of questions is not a sign of failure, but the very engine of discovery. These 30 mysteries, from the ghostly pull of dark matter to the silent drift of rogue planets, do more than just baffle us. They instill a profound sense of humility. They remind us that for all our knowledge, we are still children standing on the shore of an infinite ocean, marveling at its vastness. Each unanswered question is not a locked door, but an open invitation. It is the cosmic itch we cannot help but scratch, the whisper in the data that compels us to build a bigger telescope, a more sensitive detector, a more elegant theory. Science does not march from ignorance to absolute truth. It stumbles, wanders, and soars from mystery to deeper mystery, and that journey is its greatest glory. So the next time you find yourself under a clear night sky, do not just see a map of known stars. See the canvas of our ignorance. See the dark gaps where dark matter silently weaves its web. See the distant twinkle of a star and wonder if a strange, dusty ring or something else entirely orbits it. Let that feeling of not knowing be your companion, not your frustration. That awe is the birthplace of every great discovery. Stay curious. Follow the revelations from the James Webb Space Telescope as it peers into the cosmic dawn. Listen for the announcements from gravitational wave observatories catching the tremors of black hole collisions. Read about the new planets discovered in habitable zones and the ongoing, patient search for a signal in the silence. The story is being written right now, and you have a front row seat. We want to hear from you on this journey. In the comments below, tell us which of these space mysteries haunts your imagination the most. Is it the terrifying depth of a black hole, the eerie silence of the Fermi Paradox, or the lonely oceans of a rogue planet? Share your thoughts and keep the conversation going among fellow cosmic wanderers. If you want to join us for more deep dives into the universe's greatest puzzles, be sure to subscribe. Together, let's never stop looking up and never ever stop questioning.